to this. Okay, can everybody hear me and or chat in the room just fine?
Yes.
Okay, great. So what we're going to do here is we're going to go ahead and do our administration first. So this week we're going to finish the last little section of chapter 5, module 5, which is stereochemistry of specifically double bonds, and then I'll review all the different nomenclature associated with stereochemical names. Then we're going to go ahead and start chapter 6. Chapter 6 is we're going to first start with different types of reactions and what to look for in different types of reactions. And then when we go to 6.2, we're going to look into specific reactions like the nucleophilic substitution reactions and the elimination reactions. So, but what we're going to do is we're going to introduce the topic of chemical reactivity and energy diagrams today. So let's see, for due this week, we have homework is due for module 5 today at midnight. Note that that is the reading assignment, so go ahead and make sure you do that. So the slides are now on Canvas and they are live, so hopefully you can find them there. And we won't have anything, you don't have homework due until the end of next week. So other than the homework for module 5 that is due this week, then we'll be able to finish that up. And let's see, we did our chirality last week. I should be grading that today. So we should see the group activity scores going on to Canvas here pretty soon. All right, any questions about administration so far? Excuse me. Yes.
On the module 6A homework and the module 6B homework,
yeah,
is the amount of questions that's on there, is that correct?
Let me double check that. I thought I pared them down. So A is steeping some tea. 38 items for A. That is correct. And trying to get it to go to B here. I'm trying to keep it under 40 questions and internet is unstable. That's unfortunate. 64 items, okay. Let me go ahead and pare down a module 6B a little bit, take it down to about 40 questions, but the module 6A is correct, okay? So you can start doing the homework there. Okay, that being said, let me go ahead and pull up our last slides from module 5. Okay, oops, that's not what I wanted. I want to share. All right, I'm going to put gallery mode up over here. Okay, only 21 of us in class today. That's a little low for a Wednesday. But anyway, so, okay, where we ended last time, we were talking about how we can actually have, when we have more than one stereocenter in there, we have different things we have. We have the pair of enantiomers, which are the mirror image non-superimposable. Then we have the other possible isomers that are also either mirror image and non-superimposable, or they have a mirror plane. And when they have a mirror plane, that takes it down to one isomer. And because it's a mirror plane, it's no longer chiral. And so those are called meso compounds. But in theory, once you have a second chiral center, you should have 4 possible isomers. Unless there's that mirror plane, then you only have 3. Now, if you, of course, move on to 3, then you have a total of 8 possible isomers, and then that you have to also look for mirror planes in each of those. So you can have between 5 and 8 different diastereomers possible at that 3rd level. But now that was all with our chiral carbons, 4 things bonded to carbon. Let's go ahead and look at our stereoisomers as it relates to alkenes, okay? Now, again, the stereoisomers as it relates to alkenes is because we do not have a rotation around that double bond, so it's fixed in space, okay? So then that means we can also have diastereomers in alkenes as well, okay? So if we look at this right here, we'll see that we have all the same bond connections. However, two of the atoms have swapped positions when it was being made. Okay, so they don't actually flip back and forth. They actually had to be made this way while the double bond was forming. So in the case of this one right here, while the double bond was forming, our fluorine and chlorine were cis to each other, our bromine and iodine were cis to each other. Okay. Now, if that carbocation or whatever was flipped the other way when we formed that double bond, what we'd end up with is having two of the substituents at the same geometric location, but we have the other two that are flopped right here. Okay. And just like in the other system, these are different isomers. Unlike chiral diastereomers, they do have different physical properties. Okay, so these right here are diastereomers because they are cooked together in all the same connections. The only difference is two of the atoms are flopped in space. Okay, now if we change the way that these things are done, for example, notice on this side, the chlorine and the bromine are bonded to this carbon. And on this side, the iodine and fluorine are bonded to this carbon. Okay, and so that is the same for the other diastereomer. Okay, if we change that connection, so now we have the chlorine and the fluorine on the same carbon and the bromine on the iodine on the same carbon, it is no longer a stereoisomer of the top one because we've changed connections. Two of the halogens are on different carbons than they were in the top structure. Okay, now, but that doesn't mean that this compound here can't also have a diastereomer. In fact, if we just swapped, we kept these two exactly in the same location and just swapped these two, these now become diastereomers of each other right here. And again, because this is on an alkene, they have different physical properties, different boiling point and melting point. However, the interrelationship between the top pair of diastereomers and the bottom pair of diastereomers is not enantiomers, okay? Because they have a different connectivity, they are structural isomers, okay? Or constitutional isomers. Because the halogens have moved from one carbon to another, they are structural isomers, okay? So don't get confused when you have the alkenes, you do have the possibility of diastereomers, but not the possibility of enantiomers. You have diastereomers, not enantiomers. Okay, so that being said, we can also see stereochemistry in cycloalkanes, okay? Now, remember, when we had cycloalkanes, we were looking for mirror planes, and so we have to continue to look for mirror planes in these systems, but we can also, because rings are usually not being able to free rotate, they are fixed in space like the double bonds, okay? Like your chiral compounds, you can have free rotation, or your long chain alkanes, you have free rotation. You lose that when you have rings, okay? Which means that we could have different isomers for the same cycloalkanes because there are different places that you can put these, okay? Now, in this case here, we have this right here. We can only have one isomer for that because of symmetry. And if I draw it for you right here, we have this right here, and then let's put our X here. So depending on if you rotate it 120 degrees in any direction or flip it over and rotate it 120 degrees in any direction, they're all the same isomer because you only have that one substituent. So it's just where it is in flipping around in solution. However, by putting a second group on there, we now have isomers available to us. Okay. So the first and simplest would be put both of the different group, in this case we'll call it a halogen, on the same carbon. So if it's on the same carbon, that becomes our one carbon because it's the only substituent. And if they're both on the same carbon, that means that they have a unique way to go. So that is a unique chemical molecule. And again, if you rotate it around, it's just going to be the same. So that's just the one possible isomer. Okay, now, if we take that, instead of having them attached on the same atom, put them 1 and 2 right here, we now have a possibility here. We have a cis possibility where they are both on the same side of the ring, okay? And then we also have a trans possibility where they are on opposite sides of the ring, okay? So these are two different structures, and they have different physical properties. However, if you take this and you have a mirror plane here, you cannot have any kind of enantiomer because you have that mirror plane is in the middle of the thing and these are now superimposable. So you don't have a stereoisomer associated with this. You only have a conformational isomer for this. Okay. Now, what if we move over to the trans one here? Okay, in the trans one, because we no longer have that mirror plane, that was in this position on the cis configuration, because now this doesn't match that, we now have a possibility of creating a non-superimposable mirror image. So if we were to take this and put a mirror outside of the plane right here, and just did the exact same thing where we draw each atom in its position here, we'll see that we end up with a mirror image and they're non-superimposable, okay? And the way we can think about that is if we tried to superimpose our structure here on this one right here, we would probably try to just keep these lined up together, and then we'd have to rotate this 120 degrees. And when we rotate that 120 degrees, that would put the H here and an H here, and an H here and an X here. So they are non-superimposable. And because they're non-superimposable, they are enantiomers. So it's a mirror image that is has a non-superimposable image. So this is also a way to find enantiomers. Okay. Now, there are some weird chiral compounds out there. Okay. And I think I have a slide on those right here. Okay. Oh, okay. So if we expand that ring from 3 to 4, we can actually see we now have lots of opportunities for planes of symmetry, okay? So in the case of this 1-1 condition here, we actually can have a plane cutting through the middle of our structure such that the two halogens look the same and the two other sides here and here look the same. Actually, let me change the color there. We have our mirror plane here, and so this will look like that on the other side of the mirror, and so we have that plane of symmetry. So it's not chiral, but it is an isomer, okay? Now, if we have the 1-2, just like we had with the cyclohexane, we also still have a plane of symmetry there. Both sides match, and therefore we don't have enantiomers, but we do have a structural isomer, okay? By putting them in the 1-2 trans, just like we saw in the cyclopropane, we do see that this no longer has a plane of symmetry, and therefore the plane of symmetry is the mirror plane is outside of the molecule, and we can create a non-superimposable image from that mirror. And when we do that, that gives us a pair of enantiomers. But in the case of the cyclobutane, excuse me, we can now have an opportunity to have a 1-3 isomer. We couldn't have a 1-3 isomer in the cyclopropane because that would have been the equivalent to the 1-2. Okay. When we do the 1-3 isomer, we can get mirror planes in both the cis and the trans. And what we'll find out is that if we tried to make our mirror image here, all we would have to do was rotate it 180 degrees on its end, and it turns out to be exactly the same. So even if we didn't find this mirror plane in here, we could draw the mirror image and show that it's the same. So in this case, our cyclobutane here with 2 substituents on it has a total of 6 isomers, 6 structural isomers, but only one pair of enantiomers. Okay. Now, this brings us to the weirdest one, which is we have a chiral compound, but we have no chiral atoms. Remember, a chiral atom has to be sp3 hybridized, okay? But in the case of this special allene, an allene is where you have a double bond and then a double bond together. So they are basically linked together. Most of the time, our double bonds are separated by a single bond. In this case, we have our lone pair, our p orbital is in this xy plane sticking in and out of the plane on that one. And we have the p orbital up and down on this one. Because those p orbitals can't overlap together because they take up space, we have to use them in that 90-degree angle. And when we do that, that makes these two substituents in the plane and these two substituents behind and in front of the plane. So it's imagined that between those three carbons there, you actually have a stereocenter now. Those three carbons act as that single stereocenter, and therefore it is actually a chiral compound. And when we actually create our mirror image and do it such that it's non-superimposable, these actually turn out to be the same compound. So this technically has, these are non-superimposable, these are superimposable, but they have that system. However, if we move one of the bromines from this side of the allene to the other, we now can create a pair of enantiomers. Again, this is locked in the plane because of where the p orbitals are. This is locked in the other plane because of where those p orbitals are. And when we draw our mirror image, we have our hydrogen back, our bromine forward, and these at the same place. And if we try to rotate that around, the hydrogen and the bromine on this side would be opposite each other. And therefore they do form a pair of enantiomers, even though there's not a single chiral carbon in the system. Okay. So that's one of the weirder ones, but it does exist, and so I thought I better show it to you. Okay, so in review, structural isomers are different compounds with the same molecular formula, and they almost always have different physical properties. Constitutional isomers are the same, but have a different order of attachment. So imagine structural isomers can have different functional groups. Constitutional isomers have all the same functional groups, but are attached in a different way. Okay. Stereoisomers are different compounds that are, have the same structure and connectivity, but only are different in space. And we can have those with alkenes or sp3 carbons with 4 different groups on them. Okay, so in the case of stereoisomers, we can also have geometric isomers, and this is more likely to happen in things that are rings or on double bonds, where you can have things, because we don't have free rotation, they'll be on the opposite side, like a cis or a trans alkene or a cis or a trans ring. Okay. Chiral is specific to a carbon with 4 things attached to it, and they come in pairs, and that it has to be non-superimposable on its mirror image. If you have 4 things, but they are superimposable on their mirror image, it is not chiral, or it is achiral. Okay. Enantiomers always come in pairs. They are that mirror image, and they are non-superimposable, and they are identical in all chemical properties except for its ability to interact with plane polarized light. And so one isomer is going to go one direction, a certain number of degrees. The other isomer is going to go in the opposite direction, that same number of degrees. And therefore, by mixing them together, we can actually measure how much we have or the other based on its enantiomeric excess. Okay. Diastereomers are any kind of stereoisomers that have more than two or more stereocenters. Okay. So 2 or more stereocenters. Now that doesn't mean that if you have 2 stereocenters, you're going to have 4 different compounds because the ability for you to find a mirror plane, and they become meso. So technically in diastereomers, you'll have at least 3 isomers for 2 chiral centers and sometimes 4. And when you go to, again, diastereomers come in 2 to the power of however many stereocenters you are. So 3 stereocenters, 8 possible isomers. But each of those isomers has to be looked for to have a mirror plane to see if it's a meso form of the compound. And it's best, especially with diastereomers, to use the Fisher projection with the carbon chain up and down in the longest section to give you an idea of whether or not they look the same and where a mirror plane might be. Okay. So this is just the review we started with as well. This is a visual representation of what I started with. The structural or constitutional isomers have different functional groups. Can have different functional groups. Stereoisomers are identical except for their place in space. And we have them both with chiral compounds and with compounds that are rigid in place. And then we can have multiple possibilities with our adding a second, third, or fourth chiral center. All right, questions on the last bit of stereoisomers we have? Okay. Well, if you think about a question, go ahead and put it in the chat room, but I would like to start with module 6.1. Okay. We spent a lot of time learning a whole bunch about nomenclature and bonds and the different kinds of bonds we're going to encounter and the structure of the atom and how it relates to its hybridization. Okay. Now what we're going to do is we're actually going to start doing the hardcore chemistry where we're going to change one functional group into another. Okay. So to learn about that, we're going to go over different types of reactions we have, and we're going to go over mechanisms. Mechanism is a stepwise or kind of a time-wise list of what has to happen to go from point A to point B in a chemical reaction. Okay. So of the different kinds of reactions, these different types of reactions will be all the way through the book. Okay. We're going to see different types of reactions. And the first and simplest is what we call a substitution reaction. That means we're going to take one group and it's already on our substrate. Our substrate is the carbon chain of interest. And we're going to displace something on there and add a different functional group, or sometimes the same functional group, but with a different atom. So in this case right here, we have what we call our leaving group. This is what's going to be replaced with another atom. And then we have our part that's going to substitute it. And in this case, it's going to come in, substitute out, and we end up with our Br- and our new carbon-oxygen bond. Notice we're going from a sigma bond to a sigma bond in this reaction. Okay. The next type of reaction we have is we're going to do an elimination reaction. This happens when you eliminate one thing from one atom and one thing from a carbon adjacent to it. Now, typically we call this the alpha carbon because it has the better leaving group, and we call this the beta carbon because that's where the other atom's coming from. It's really common to have something like bromine and hydrogen leave because that leaves as an acid. Sometimes you can have oxygen and hydrogen and OH leave as water. So we have different types of elimination reactions, but you typically liberate something that is a neutral species during this. And when you do that, you go from you taking 2 sigma bonds and turning that into a single double bond. Okay, so we're getting a pi bond out of the system. So elimination reactions eliminates 2 sigma bonds and creates a pi bond. Okay, now it always happens with 2 adjacent carbons. Okay, the next kind of reaction we have is the opposite of elimination. It's addition. We're going to add something across that double bond. And we can add water to it. We can add HBr to it. We can add anything. We can even add hydrogen, 1 hydrogen to each side. The key here is we're going from an sp2 hybridized to an sp3 hybridized. So we're going from our pi bond to all sigma bonds. Okay, so addition reaction. Okay, the other thing that can happen is what we call a rearrangement. Okay, so a rearrangement happens when you take it from one form and turn it into another isomer, but keeping all the bonds in about the same place, except for you have a different isomer from the original product. So one way we can think about that is if we have this stereoisomer, the cis-alkene, we know that we can temporarily break that pi bond and have it swap around and then reform that pi bond in the case with an acid catalyst, okay? And in that case, we go from the cis to the trans, so they are no longer the same compound. However, they are structural isomers to each other. They are all the same connections. And this is what we call a rearrangement reaction, okay? And those are sometimes useful if you want to do different chemical substances. Okay. Now, this one we're going to look at is called bond cleavage. Okay, so this happens in a couple different ways. Okay, there's heterolytic cleavage, hetero meaning different, and so meaning that one atom will lose electrons and one atom will gain electrons. So in the case of the heterolytic atom, the electrons that are forming the sigma bond between the carbon and whatever your leaving group is, those electrons usually leave with the leaving group, and therefore it leaves a charged carbon. And we'll talk about carbocations in a minute. And this, so it's hetero because one gets all the electrons, the other one doesn't, and you end up with two different charges. Okay, so the other way to do this, and we'll talk about this in module 10, which is radical reactions, is what we call homolytic cleavage, meaning that, okay, I'm going to break that sigma bond, but I'm going to keep one electron on one atom and take the other electron on the other atom. So we're taking those two sigma electrons and each of us get one of them. And so we form what we call radicals. And so this is homolytic because they each take away the same number of electrons from the system, okay? Now, in general, bond breaking tends to be endothermic, meaning it absorbs heat to do this, okay? So that the energy that was in that sigma bond is being consumed in the system. And we'll talk a little bit more about endothermic and exothermic in a little bit. Okay, so then if bond breaking was one type of reaction we're going to see, that means bond formation is another thing we're going to see. And then in bond formation, we have, again, the same kind of two different kinds. We have the one where both electrons that make the new sigma bond come from one of the two species. And so you typically see this in reaction with an electrophile and a nucleophile. An electrophile usually has a positive charge or wants electrons. A nucleophile usually has a negative charge or has extra electrons to make that new bond. Remember when we talked about Lewis acid, Lewis base? The Lewis acid is the one that is wanting to accept electrons. So our electrophile is a Lewis acid. Our Lewis base is the one wanting to give electrons to make that new sigma bond. So our nucleophile is the Lewis base. And because the Lewis base is bringing in all the electrons, we call that heterogenic, or making it with electrons only from one system. In the other process, if we have, each of us have one electron, we can use both of those to form a new sigma bond. And this is homogenic because we each had an electron that we're adding to that sigma bond, and therefore we're bringing the same number of things to it. Notice if breaking bonds is endothermic, meaning it takes energy to do it, bond formation tends to be exothermic and gives off heat while doing it. Okay, so bond formation is exothermic, but bond breaking is endothermic. Okay, so how can we follow this? Okay, we typically follow this by what we call an energy diagram. Okay, so an energy diagram is just a way of looking at the potential energy of the system as we go through the reaction. Okay, so if we can think about the reaction pathway as just, following one molecule as it's going through all the different changes it makes during a reaction. okay? So in the case here, we have potential energy. And you can think about this as all the different bonds that are added together. They each have a little bit of energy associated with it when you form them, okay? And when you break them, you have to give up some of that potential energy. You have to absorb energy to get them to do that, okay? So if our reactants right here have this much potential energy, okay, when we start the reaction, and then as we move across the reaction, we have to absorb some energy to get it to break that bond, because it's endothermic, so we have to absorb some energy to do that. And then the new bond we form actually has less potential energy than the reactants we started with. It gives off heat because it has less potential energy, therefore it has less stored energy, and it's going to give that energy away as heat. And we call these exothermic reactions. So these are reactions that heat up by themselves as the reaction progresses. Now, the opposite of that would be if your starting materials have very little potential energy, and you have to add energy to the system to get it to go through that change. So we're like trying to break some bonds, and we have to add a lot of energy to break those bonds. But then the new bonds that form actually have a greater potential energy than the starting materials did, and therefore it absorbed heat in the system. And that means your new product has more energy in it, which means it's an endothermic process, meaning you had to add heat to the system to get it to go, okay? So in an exothermic reaction, once it starts, it can actually self-heat itself because of the heat released. Endothermic reactions, you have to continually add heat or they'll cool down and slow down. All right, questions about energy diagrams. Energy diagrams help us kind of understand what happens to individual molecules as we start getting them to react together. Okay. All right, so let's talk about the dirty word thermodynamics. So the whole concept of thermodynamics is you kind of want to look for what's happening in the system, okay? And so to tell whether a reaction is going to go or not, or how much heat you need to put into a reaction, you need to understand the difference between the energy of the reactants and the products. And in this case, we're talking about the free energy, meaning that there is, the difference between the potential energy gives us our energy that we'll see in that reaction. So in the reaction, if we're converting our products and we can determine the difference between these energies, the starting energy and the ending energy, the one we're going to look at first is called Gibbs free energy change, or the change delta G0, okay? So in the case of the change in free energy, if it's positive or negative, will tell us whether the reaction is going to be favored or not favored. Okay. So in the case of an exothermic reaction, we actually can have, I'm sorry, not an exothermic. Here, we've changed the energy diagram. And instead of being potential energy, we're looking at the free energy of the system, okay? When we're talking about the Gibbs free energy, we're not talking about heat. So when we saw the previous diagrams, we were talking about the heat released was exothermic, right? In this case, we're talking about the free energy, and the free energy is associated with, being able to have molecules that are freer to move, et cetera. Okay, so we think about it as a mode of freedom, of free energy, okay? So if we start with our materials here and they have a particular free energy, and you go through this change such that it comes to products, and that change in energy is less than zero, meaning you give off the free energy, then it's called an exergonic. Gonic means is the free energy component. So it's exergonic, not exothermic, okay? So exergonic means it's giving out free energy, okay? Which means the opposite of that would be endergonic, where it would be you start with your potential energy, your Gibbs free energy way down here, you go through your transition state and you end up here, and that would be a net positive gain of free energy, and that would be endergonic reaction. Okay. So, but most commonly we'll talk about why we do that. All right, so we have to figure out the difference between the equilibrium constant, or whether the reaction is going to go forward or backwards or stop somewhere in the middle, and that change in free energy, okay? So we actually typically measure this to help us find what our free energy is. And so our equilibrium constant right here is equal to the concentration of the products divided by the concentration of the reactants. So as the concentration of the reactants decreases, your number goes up. As the concentration of your products decreases, your number goes down because they're higher concentration. So in this reaction mechanism where we have A reacting with B, so a nucleophile reacting with an electrophile. Oh, in that case, we only have one product, but let's say we're doing a substitution reaction. And so we're going from compound A, and then to our substituted compound C, and then we give off something else. We have to look at the concentration of each of the components of our products, the concentration of each of the components of our reactants, and divide those. And that gives us our equilibrium constant. Okay. But that equilibrium constant only gets us so far. We can't really calculate the Gibbs free energy without using temperature and the ideal gas constant right here. So we can calculate that change by looking at that, by taking the natural log of the equilibrium constant, multiply it by the temperature in Kelvin and the ideal gas law, and that gives you the change in Gibbs free energy. Don't worry, you don't have to calculate this. You just have to know that it exists. Okay, so what does this mean? So the relationship between the equilibrium constant and the Gibbs free energy means that the change in Gibbs free energy determines the max yield of your products, okay? Because the equilibrium is going to shift to a certain point and then it's going to stop, okay? So let's say you have a very big equilibrium constant, meaning that it wants to favor products. That means you're going to have very few starting materials left, okay? Let's say your equilibrium constant's not that great. You only can convert half of your species to the product, and then the reaction stops. Okay, so that's why the change in Gibbs free energy determines our max yield of our products, our maximum. Okay, so in general, equilibrium always favors the more stable species or the species with the lower potential energy. Therefore, if the change in Gibbs free energy is less than 0, the products will be favored at equilibrium, okay? The energy of those products is lower than the energy of the reactants. So you can imagine that if we looked at our energy diagram, the starting materials would be here and the products would be here. That makes it give off Gibbs free energy, and it's exergonic. And that means that it's spontaneously moving from that higher energy system to the lower energy system. Okay, that's where we're looking at. This makes it a spontaneous reaction. Now, if it's the other way around and it actually favors the starting materials and the products, your equilibrium constant is less than 1, what is going to be saying is this is not going to be spontaneous. You have to add energy to it to make that free energy change, okay? So we call this endergonic, meaning that we are actually lowering the free energy in the system by having to make it go by some other method, like by heating or by using light or using something else. So exergonic are spontaneous reactions, and endergonic are not spontaneous reactions and have to have some other influence making them happen. Okay, so before we talked about that change in heat, whether it was the exothermic or endothermic, well, let's talk about how that kind of relates to each other. Okay, so the total free energy of the system, or the change in free energy of the system, is equal to that change in enthalpy, which is the heat of the system, minus temperature times the change in entropy. Okay, so let's imagine you have two reactants going to two products. Okay, there's no real change in entropy in that system because you're going from two atoms to two molecules to two molecules. But what if you had a molecule that you were in the process breaking it apart? So you started with one molecule and you end up with 10 molecules. You've increased the disorder in the system. Therefore, the change in entropy becomes significant. Okay. Now, it's also dependent on temperature. Okay. So when you have very high temperature reactions, you're likely to fragment things into a bunch of radicals, and therefore it becomes more important. However, most of the time, we can actually have this be that the Gibbs free energy is approximately the same as the enthalpy of the reaction. And the enthalpy of the reaction is actually much easier to measure because you could measure that change in heat of the system. Okay. So, generally, we can say that our Gibbs free energy, oh, that's the other thing, yeah. Our Gibbs free energy tells us whether or not the reaction is going to be spontaneous or not, okay? And if it's a spontaneous reaction, it tends to give off heat, making it exothermic, okay? So the heat, the energy that was stored in the bonds is given off during that system, okay? And if it becomes more disordered, like breaks into parts, then that is also accounted for in that entropy process. Okay, a spontaneous reaction will not occur if the enthalpy of the system is positive, i.e. you have to absorb heat, and there's an increase in the entropy as well. Okay, so those will not happen. So that means most of the time, okay, reactions are spontaneous when your change in enthalpy is negative or it gives off heat and your entropy doesn't change. Okay. So that leads us to this kind of generalized rule where the conditions that favor reactants are where you have a very small equilibrium constant. You have an endothermic reaction. You have an endergonic reaction, and you're increasing decreasing entropy. So those mean that the reaction is less likely to go. Okay. So, but if the conditions favor the products, that means your equilibrium constant is much greater than 1. It tends to be exothermic. It tends to give off free energy, and it tends to decrease entropy. These are the conditions that help us drive a reaction to completion, and that's what we'll see in the system. Okay, so how do we use this? Well, we typically don't do any of these calculations. We typically just look at our energy diagram, and our energy diagram tells us all these things in a nice visual manner. Okay, so in this case here, let's look at a reaction, and we're going to say that this reaction happens in one step. Okay, so the only thing that happens is your reactant go and they have a certain amount of energy. Let's start with that. We have a certain amount of energy associated with our starting materials. And we're going to go ahead and add a little heat to the system to get the reactants to come up to react, okay? Just sitting in the reaction mixture, they might not react completely, but when we heat them up or give them free energy, that energy of activation, they go into the place where they can, the one bond from the reactant is starting to form. The leaving group from the reactant is starting to leave. We have this imaginary transition state, okay? It happens for an infinitesimal second. One bond is forming, one bond is breaking, and then hopefully that means that you're going to give off energy in the product either as free energy or as heat, and that new one will come down. So if your reactants are higher in free energy than your products, you have a positive free energy change, and you have an exergonic reaction. Now, so you can tell it always because look at where the relative energy, either the free energy or potential energy, is above the products, then we're looking at something that's going to give off energy or give off heat. However, the opposite is true if your reactants start low and your products are up high. Okay, Notice it took a lot more energy of this activation energy to get it to go to that transition state. And we get less of that energy back when it goes to product. And so our change in free energy here is maybe the same, but we had to use a lot more energy to get it to do that. Okay. So 3 things to remember about these type of energy diagrams is you want to look at the product to reactants and the height of this activation energy barrier right here. All right, questions on that? So these energy diagrams actually tell us a lot about what's happening in the system. And in particular, this particular energy diagram says we only have one step in our reaction. It goes to that bond breaking, bond forming, and then it goes to product. Okay, is that how they're all going to be? No. Okay, where did it go? That's not right. Sorry, hit the wrong button. Okay. All right, so here's where we were. So those are the different parts of these energy diagrams that help us decide how the reaction is going to go and whether or not it's going to go to completion. Okay. So in this case here, we're going to talk about a substitution reaction. And in this case, we're going to take a hydroxide ion here, and we're going to displace a bromide ion on it to create a new compound, a new carbon-oxygen bond, and liberate the anion bromine. Okay. So this is a substitution reaction, but it happens in one step. Okay. We start with our potential energy of our materials, and then we have to heat it. We have to give it some kind of activation energy to get it to go to this transition state. And that transition state doesn't exist. We can't see it. It happens so briefly, it's really hard to measure, but we know that one bond has to be forming the same time one bond is breaking. Okay. Now, once we get to that point, it'll come down here and give us our products, our new sigma bond and our new ion. And if it gives off heat, if our potential energy is lower here, that makes it exothermic. Okay. And so that means this happened all in one step. All you had to do was add component A, component B, and some kind of energy to overcome that activation energy barrier. Okay. Now, what would it look like if it actually took place in 2 steps? If it takes place in 2 steps, that means we have to have 2 different activation energies. And we form what we call an intermediate. An intermediate is a highly reactive chemical species, but it lives there long enough that we can actually measure it by some kind of spectroscopic method, either NMR or IR or something like that. Okay, so in the case of this compound here, we have an alkyl halide and we're trying to substitute it with a different halogen. So we wanted to get rid of the bromine and add that chlorine to it. So the first thing that has to happen here is when we'll find out that we can't do it in one step, the first thing that has to happen to is we have to do one of those things that we can do, which is break a bond. We have to break that bond first. And when we do that, we form this intermediate. This is a charged carbon species called a carbocation. And then it has to overcome a second energy barrier to start forming that bond. So this is breaking the bond, and then this is forming the bond. Okay. And so we have a second, usually smaller activation energy to do that. And then when we get to our products here, we see that our potential energy from our starting materials to our products drops off, meaning it's exothermic. So you can always tell how many steps you have and whether or not you form an intermediate by looking at the reaction diagram. All right. All right, so I'm going to stop with reaction diagrams today, and then we'll move on to kinetics and how fast the reactions run on Wednesday. Questions about reaction diagrams and how to understand the idea whether it is exothermic or endothermic, or exergonic or endogonic. Okay, I'll go ahead and stop recording, and then you can freely ask questions until you have to run off to your next class.